So today I want to show several flash mitigation techniques. I am going to be using this model I've previously set up, and everything is set up in different revisions or scenarios depending on how you call them. I'm going to be using ETAP, and what we're going to do is we're going to start with a very basic. Don't get too lost on the system. The system is rather simple, and it was done as simple as possible because the purpose is just to show the different our flash mitigation incident energy, not our flash mitigation. Let me rephrase that: incident energy mitigation techniques. So let me do a quick description of the system. This is a very typical system. So let's just assume up here we're gonna have some sort of 4160 5 kV. It could have been a 15 kV system of any nominal voltage. It's gonna be out somewhere in the yard. We're not gonna get too concerned with that right now. Let's assume there's gonna be a fuse hanging from some bus in a switch somewhere, and then from there you run 100 feet of cable, and that 100 feet of cable goes to a full setup of unit substation. And by a full setup of unit substation, I mean some sort of disconnecting means on the primary of a transformer, typical step down transformer for industrial use at 480 volts. And then from there it's going to be coupled to some bus duct, and that's going to take it down to some form of switch gear on the 480 volt side. That could be a switchboard or a metal enclosed or a metal clad switch gear. For now I'm just setting up some simple bus. I'm calling it switchboard 1, and it's going to have a main. I'm going to make that main a power circuit breaker, and then I'm going to have molded case breakers feeding different, let's just call it machines for now. It could be an MCC line up down here. I'm writing drive cabinet because lately that's something I've seen proliferate in industrial environments where MCCs are getting replaced by drive cabinets, and it's a different discussion, but it gets simpler depending on the application. So we're going to have 3 feeders down the 480 volt side. We're going to have a main in that switchboard, like I said, power circuit breaker in that switchboard, 30 foot of bus duct. All this assembly, I tend to call all this assembly, and I may be wrong in here, but I tend to call all this a unit substation. And by that I mean is the typical drop you will have in an area of an industrial huge plant, but you're gonna need 480 volt at some point somewhere, or 4160, or any other voltage that you need. And it's just going to consist of that disconnecting means on the primary side, a step down transformer, power transformer, and then the distribution system of some sort on the 480 volt side. Go through the system right quick, element by element. This is just going to be a regular fuse. A typical SNC fuse, 400 amps rating. Then I'm going to come down with a cable. What am I saying it is? It's a number 4 aught, 33% EPR, 33% insulation, so just a standard cable. And then I'm going to come on the primary side. And for now, the breaker doesn't exist. It's just a dummy breaker, because what I'm assuming is all the protection is done by this feeder fuse up here. And well, I just have to have the breaker in there because I'm going to use it later on the other scenarios. But what in reality will happen is this cable will be terminated on the primary of that transformer, and maybe the transformer has some bayonet fuses in it for overload protection, but there is no disconnected means. There's gonna have there's gonna be a switch disconnected means in the transformer, but you know, in modeling, for modeling purposes, I normally don't waste time putting switches in there that are not gonna affect my modeling anyway. The transformer is gonna be a standard. What did I say it was? It's going to be a 1500 kVA, OAFA 65. Temperature rise, so you can overload it up to 1725 MVA, and then it's gonna be typical just liquid filled mineral oil, standard impedance. Just a standard transformer is gonna be coupled to a 2000 amp service through a bus duct, just a standard bus duct, 30 foot of it, and then I'm gonna hit this bus in there is just to have a point where to calculate the line side incident energy of this protection of this main breaker. A main breaker is going to be an Eaton Cutler hammer Magnum DS, and it's going to have a trip unit. What is it? What did I say? It's going to be a 520. Trip unit, a Digitrip 520, and I have locked. I didn't worry about ground settings because I'm not doing any coordination of any ground coordination. I'm just concerned about our flash for this simple model. I'm gonna show the TCC later on, but I think everything is coordinated with the fuse as if it was typical. And then the maintenance is just waiting in there for me to do something with it. I'm just gonna leave it in there. But for the basic scenario, there's no maintenance switch on it. And the ground, I didn't even look into it because it's not the purpose of this video. Then I'm gonna come to my 2000 amp distribution section. And what do I have for feeders? Well, I have electronic trip units, 310 plus, and all of them are gonna be, this is end frame. Cutler hammer end frame, a molded case, and I think all three of them are the same. Let me check. Yes, all three of them I made in end frames, 1200 amp frame or 800 amp frames. Did I make them all 1200 amp frames? Believe it or not, I'm looking at all this again. I believe they are all. No, this is an 800 amp frame. This is a 1200 amp frame. Alright, and then the cables are pretty standard. I hope I sized the cables correctly. If I come here, yes, well, that's gonna have a derated rating of 1143, but I'm not gonna get into the rules of sizing feeders right now. Not the purpose of this, but I'm just gonna check right quick. 762 derated, 620, and it must be that the trip unit in here is set at, what's the trip unit in here set at? It's set at 600 amps. Okay, so that's what I'm doing. This is a 600 amp feeder, what I have in here, and this is what do I have here? This is an 800 amp feeder. And this is a fully rated 1200 amp feeder. And down here I'm just gonna have drive cabinets. Let's assume that that's just the termination of the cable in the drive cabinet, whatever that is, whether it's a switch or it's a breaker. What do we have? We have it in here. Like I said, there is no, the base case is just the fuse, and it's just the breaker with the typical phase settings on the trip unit, and I am going to pull, I hope I saved it. Yes, I did. So here's the standard coordination. It's just a standard phase coordination. The fuse is on the primary, and it's gonna allow for the main to trip first if necessary. This is the main in red, and then all the little feeders are downstream of the main, and we have to assume that they are coordinated with whatever is on that drive cabinet. So that's the standard of a current coordination. No extra feature. We are doing all our flash calculations based on that standard coordination. So the first case, let's go to our R flash. Let's do the first one. We're gonna run this. And do I wanna fold everything? Yes, let's just fold the whole thing. Okay. And then let's turn on the data blocks. And I'm not concerned about the primary. The primary is not going to change through all of these. Well, yes, it will. Let me rephrase that. But I'm mainly concerned, like I said, about the secondary on that transformer, although you shouldn't have much to do on the secondary of that transformer while energized, and the line side of the main. Oh, and by the way, I'm not gonna go through a whole electrode configuration setup. It's just set up. If I go through it and start describing, I'm gonna waste too much time on it. So just trust me, it's set up. What do we have in here? We have about 70 calories. So that's what we get. We get 70 calories on the line side of that breaker. Now, what's that breaker doing to those incident energy once it goes through the load side of it? It's taking it down to about 8.6 calories. All right, and all of this is at 18 inches, by the way, working distance. Oh well, the line side is a power circuit breaker, so I set it up at 24 inches. Assuming you're racking. If you do it at 18 inches, it will be worse. So we have 70 calories on the line side, and we have about 8.5 calories on the low side. And then down by the drive cabinets, everything is kind of a very low incident energy, 1.3, 1.7 or 1.8, 2.7, nothing to be concerned about. All right, that's just a straight overcurrent coordination. What's the next thing we're gonna test? Okay, we're gonna go back to edit, and we're gonna turn this off. And the next thing I wanna do is I want to do an arm zone, and that is the R flash reduction maintenance switch in this breaker. And the way you do that is, the breaker, in the case of this Eton one, they have a contact input, a relay input on the side of the breaker. You can wire to a selector switch, and you engage that selector switch. And Eton actually sells these things already wired and everything when you order switch gear and switchboard from them. Any equipment you order for them, you can always include those options. And what you do is you just go and flip that selector switch, and that brings the maintenance switch in place. And the maintenance switch, all it is, people have all sort of fancy descriptions for it, but it's just an instantaneous override. You're gonna see it now on the TCC coordination, and that instantaneous override, instead of just being a normal instantaneous, I don't know exactly how they make these things, to be honest with you, but it's got a much shorter time band. So if your typical instantaneous might be it might have a band of about, I don't know, 5 cycles. These things, they make it like 2-3 cycles. And I may be wrong on those numbers, but we're gonna say it now on the TCC. But that's what it's doing. It's just engaging that instantaneous override. The problem with it, of course, is, and you're not gonna see it in here because we don't have any across the line motor loads. The problem with that is it's gonna miscoordinate with everything downstream of it. And maybe that's not a problem. Maybe everything you have on this switchboard is just simply part of the same machine. And if you lose drive cabinet 1, you don't have a reason to have drive cabinet 2 and drive cabinet 3 going on. So it's just a matter of, well, if I need to trip, let's just go trip the whole thing. I don't care if it's miscoordinated, but that's not always the case. Sometimes you miscoordinate with a maintenance switch, and if you leave it on, and you never go back and turn it off, and you don't put it on some sort of delay timer, or you put some sort of indication back to some DCS system that thing is still on, well, your system is going to be miscoordinated. And maybe you do have a reason why, if this feeder was to have a fault, you might want to isolate it just to that feeder breaker, the 1200 amp feeder breaker. And you don't want that thing to take out the whole switchboard and consequently all three machines. Maybe these three machines are independent processes. So you have to be careful about how you use and abuse that maintenance switch, because I've seen it used and abused all the time. So I am on that one, and I am going to pull the coordination up again, and this is what I was telling you. See, this green band over here, it goes to about 0.03, 0.0, I want to say it's about 0.04, and 0.04, that's about 2.5 cycles. So I'm gonna go back and leave it on arms, and I am going to go back to my model and run my new OR flash under this maintenance switch on scenario. And again, we'll focus. I personally am focused on the switchboard and maybe the secondary of the transformer. So I'm not going to spend too much time on the primary side where there's going to be a breaker. Well, that breaker for now is just, like I said, it's a dummy breaker up to now. Please don't show this again. And there you go. The primary side, nothing happened. You still have the same problem, because our arm switch, I forgot to mention this, but of course our arm switch is just intended for the worker to go work on the distribution section of it. It was about 8 calories, and now it's going to be, let's zoom into it, it's going to be about 1.6 calories. So that's the arms scenario. Everything is gonna get, basically all the incident energy is gonna go down as far as that arm switch can reach down in the system, you know, down into those trophy cabinets in this case, and down in the distribution section of the equipment. So like I said, it was 8 calorie or 8.6 calorie before. Now the distribution side of it is at 1.6, and down by the drive cabinets it changes, but I think it's about the same numbers it was before. Next scenario, what I'm gonna do is some selective interlocking. You're gonna implement a some selective interlocking. You make sure everything in there is from the same manufacturer. Everything is being tested by the same manufacturer. Everything goes together, and the manufacturer can vouch for it. Eaton, for instance, everything here would have been Eaton. And the point of it is, well, it's just a way of telling the main that if you see a fault, you need to have some sort of permissive from the feeders. Because if one of the feeders is seeing a fault, that means you need to give the feeder a little bit of time to take care of it. When you do this with relays, with microprocessor-based relays on medium voltage and high voltage, it is beautifully done. It's very simple to do, because relays are kind of like computers. When you do this with multi-case breakers and power breakers and all that, well, you need to buy whatever the manufacturer is selling to you, and you need to understand exactly how it's done and how that equipment interacts with each other. So for instance, the Eaton one on the 520, the some selective interlocking that goes with the 520, that thing doesn't work on instantaneous. That thing only works on the short delay band. So you're gonna see it now on the TCC, but it doesn't work with the instantaneous. So you couldn't have a fault that falls in the instantaneous between this feeder and this breaker and have a some selective interlocking scheme going on. It doesn't exist, as far as I know, for Eaton at least. It needs to be on the short delay region of the coordination. Now, the explanation for that might be very simple. The explanation for that might be that these breakers, when they come from the same manufacturer, in the majority of cases, they've been tested to be selectively coordinated in the instantaneous region. That means that When they run 10,000 tests on these things, they can almost guarantee that the feeder instantaneous is gonna trip way before than the main instantaneous in that combination. That may be the reason why, but let's go to the TCC, and here you're gonna see it. Now you see that green light in there? That green light in there is the way of telling you I got some selective interlocking going on between the main and the feeders. And that's exactly what I'm gonna happen if I have a fault downstream of one of these feeders. The feeder is gonna block the main from tripping for a while. And after that, only after that, the breaker, the main power circuit breaker is gonna trip. And in that way, you can be quote unquote miscoordinated, and still you can isolate the faults downstream of a feeder. So let's go and run that. We go and run it now on some selective interlocking. Run our flash. I'm gonna have to do some heavy editing in this video because it's getting too long. So now what we have is kind of a similar situation. The arms, not the arms, the main breaker is on a some selective interlocking arrangement with the feeders, scheme with the feeders, and the incident energy is not going down. The incident energy on that cabinet, on that enclosure where the main is not going anywhere. It's still gonna be that very high value of 70 calories per square centimeter. And on the load side of it, in the distribution section of it, it's going to go down to 1.2. So it's about the same thing as arms. The only difference is that now you can have that little bit of miscoordination, but still the feeders are going to be able to isolate the fault without having to treat the main. And if you were to have an incident on the bus, the main is going to trip immediately because all of the feeders are going to be impermissive to the main on that some selective interlocking. So you get both. You get a level of coordination, and you also get low incident energy on the bus distribution without having to sacrifice coordination. I'm going to move on to the next one. What I'm going to do here is I'm going to start with a virtual main. And what a virtual main does now, I don't have any TCC to show, but what a virtual main does now is it's going to engage this relay, which I think I made the 751 typical Schweizer relay. And what that's going to do is just going to be looking at it's going to be another instantaneous override, but it's just going to be looking right at the transformer. So you put your CT right on the transformer. Now, if this bus represents the transformer terminals, well, does it go upstream or downstream of this CT? That's a discussion about how the transformer is being built. Now, this virtual main is pretty popular. Everybody's doing virtual mains these days. Everybody just goes and throws 3 CTs on the faces, secondary faces of that transformer, and buys a relay. The good thing about Schweizer, I don't have the numbers in there, but I'm gonna post it on the video when I edit it. The good thing about Schweizer is they got very fast output contacts, and you can put your trip equation on one of those very fast output contacts, and that thing is like fast. I mean, compared with regular output contacts, that thing makes the difference when it comes to arcing time on your calculations. And I am gonna update my calculations, and now I should see some improvement. And here's the improvement right there on the line side of your main. You went from 70 some calories per square centimeter to about 4.7. That is significant. That is the beauty of that virtual main. That's why everybody's doing it. It's just a simple solution to deal with our flash. What's the problem with it? The same problem you will have with an ARMS. You have to miscoordinate. So the people I've seen doing this, they usually associate this transformer with a process that the whole transformer covers the whole process. If you were to trip this machine down here on drive cabinet 1, the process will stop. Anyhow, the PLCs or the DCS, whatever they're using, was going to trip the whole process. So drive cabinet 2, drive cabinet 3 didn't need to stay on. They didn't need to stay energized. So there's no need for coordination. The problem is, of course, again, when drive cabinet 1, drive cabinet 2, and drive cabinet 3 are independent processes. And you don't want to trip the whole thing. Well, now your virtual main becomes a sticky point. You have to deal with it. Yes, it solves your R flash issue, but now you're gonna start having reliability issues if you have a small fault that is not gonna result in an R flash. Well, it's gonna trip your whole thing. So you need to be reasonable about that when you do this. So I forgot to say something has to trip. Of course, this relay, the trip output on this relay is going to trip the primary side, and that's when the breaker comes into play. You got to have a breaker for isolating that primary. You got to do some trip on the primary side, energizing that transformer. So maybe this breaker is not next by the transformer. Maybe this breaker is upstream in a 5 kV switch gear that fits the whole plant, or a 15 kV switch gear feeder somewhere upstream. That's not the point now. The point is you need to go and trip on the primary because you need to interrupt the whole energization of the transformer. So that's very popular, virtual main. So the last alternative I'd like to discuss is a transformer differential. It's actually a transformer differential that wraps all the way around the main feeder and down to the load side of the main breaker in the low voltage distribution side of it. So for that, what we're gonna do, I've already set up. We're gonna come to this little scenario I previously set up, and what I'm doing in here is I'm bringing this 787 relay, and the 787 relay is set up only for the differential portion of it. It could be set up for the backup of a current into the primary of the transformer as well, but for this case I'm only setting it up for the differential of it. Now a little bit of a disadvantage with this differential is compared with the virtual main is the processing time. If you take the processing time of the previously discussed virtual main, that was a Schweitzer. I'm looking at the specs right now on the side, and it's for the 751, the IOC element PAF, that's between 2 and 5 milliseconds processing time. That's about a quarter of a cycle. So that's a very fast processing time for that phase and neutral. They call it PAF and NAF in Schweitzer 751s, and it's basically the instantaneous. That P stands for phase, and the N for neutral or ground is basically R flash, PAF for R flash, and it's a very fast processing time. Here on the 787 on the other side, I'm setting up about 3 cycles, and that is the worst case, but as you can tell, it's a little bit slower on processing time. It could be faster. If it's on restraint, it can be about 2 cycles, up to 2 cycles per the specs on the 787. If it's a restraint differential, it can take anywhere between, I'm looking at the specs, that's why the sharp numbers, right? But 2.62 and 2.86 cycles. So that's why I'm giving it about 3 cycles of processing time. So that's one of the little disadvantages. Sometimes it does make the difference when it comes to processing our flash. So we're gonna go to our flash, focus, and we are going to hit again, round, and let's see what the numbers are now. So we go to the line side of that main breaker, and now it's about 4.7 calories per square centimeter. So it compares pretty well, to the virtual main, and of course it's much better than just a straight away current protection and standard with current protection. And down here, it probably will be whatever it was on the main, down here by the main cabinets, and down here by the distribution is still gonna be driven by whatever I do on the main breaker, right? So in this case, I think that I left the main breaker on, I am pretty sure I left it, I left it on some selective interlocking. So downstream is doing whatever it was on some selective interlocking. So the numbers will be the same downstream of the main breaker as if it was on the scenario under some selective interlocking. The only difference, of course, then is on the line side. The line side is much improved under this differential, and that cabinet where the main breaker is now can be labeled at about 4.7 calories per square centimeter at 24 inches working distance. Now the same thing goes for the secondary bushings on the transformer. And do notice that I have the virtual main disabled in this scenario. And we haven't touched about this, but you can always see that the primary termination on the primary breaker coming from the substation, that will never change. Whatever I do downstream, down here by the unit substation, those numbers are always going to be determined by whatever it is on the substation fuse, or if you have any other feeder breaker with another protective relay and protection up here, that's what's going to determine that R flash number. So that is the differential alternative.